Good morning, everyone. Let us continue with our discussion on optical isomerism. So, in the previous class, we looked into the compounds with one asymmetric center. So, today we will look into compounds that contain more than one asymmetric center. Since we are the complementary class, we will be going only up to two asymmetric centers. Now, before I do the discussion, I would like to say that those who are not familiar with the drawing of the two-dimensional formulas, please go back to the various previous videos and understand that, because only then you would be understanding what I'm discussing here in this particular video. So make sure you look and understand all the previous videos before you come to this particular video to understand what I'm discussing right now. Okay, so let us go into the compounds which contain two asymmetric centers. Now, this was the compound that I discussed in the previous class containing one asymmetric center. So this is your bromo, chloro, fluoro, methane. Okay, this I have drawn in a Fischer projection manner. So this is the compound with one asymmetric center. So if I want to write it in terms of perspective formula, you can write something like this. So since I'm bringing it here, this will be coming here and this will be going here. Obviously, you have to first convert this into this particular formula. BrCl, and your vertical dash bond will contain F and H. So H is on the top and you bring F here, Cl will be coming onto the left side and Br will be pulled inside. So that's why I drew like this. So this would be your perspective formula. So this is the compound with only one asymmetric center. Now let us look into this particular example which contains two asymmetric centers. Now if you want to name this compound, so this is your carbon chain 1, 2, 3, 4. So it is a bute. So there are two substituents, two hydroxy groups attached at 2 and 3 position. So it would be 2, 3 butane diol. 2, 3 butane diol. So that is this compound, and as you can see, carbon number 2 and carbon number 3, they are the asymmetric center in this particular molecule. So I'm trying to draw initially the perspective formula for this compound. Now, with multiple compounds with multiple asymmetric center, what you have to keep in mind is that it is not very easy to always draw the perspective formula. So when it comes to multiple asymmetric center, we always prefer to use Fischer projection formulas. Okay, so that is why I'm just going to show you how we converted a perspective formula into a Fischer projection formula, but here onwards I'll be only using Fischer projection formula because they are more simpler to understand and represent also when I talk about multiple asymmetric center. So I won't be discussing further this perspective formula because this looks little complicated. For two asymmetric centers it's still fine, but when you come to more than two, it would be very difficult to each time show the conversion that is happening. So we will be concentrating only on the Fischer projection formula. But today I'll show you how this perspective formula can be converted into a Fischer projection formula. So this is the perspective formula for this butane 2,3-diol. Okay, so what I'm going to do is I'm going to convert it into a Fischer projection formula. So as we did in the ones with one asymmetric center, same thing what we are going to do with two asymmetric centers. So here, if you remember correctly, we have first converted this this perspective formula into this kind of formula. Because when we convert it into this formula, you can directly write the Fischer projection formula. So what I am going to do is, I'm going to construct a formula something like this. These are my solid wedges. Okay. So I'm going to place my two solid, the if I number this carbon atom, 1, 2, 3, and 4. Okay, so what I did is I have kept this CH3s on the vertical sides. Okay, and these substituents are the ones that will be coming on the solid wedges. So how do we write the substituent? So this particular thing, as we did in these cases, these line bonds, I have kept it in the vertical bonds. Okay, these line bonds, I have kept it in the vertical bond of this particular flying wedge formula. Okay, so in this case, what do you see? I have kept the CH3s on the vertical bond. Now I have to put the substituents here, how it will come. So I'll concentrate first on the second carbon. Okay, so if I concentrate on this second carbon, and if I rotate my molecule along this particular C1, C2 axis, this particular axis, if I rotate by anti-clockwise, what will happen? This OH will be coming on the right side. So OH will be coming on the left side. So automatically this bond will be having my H. Okay. Now let me look at the second asymmetric center, that is carbon number 3. For for conversion into this particular way of writing, what I have to do, I have to consider this particular axis, that is C3, C4 axis, and I rotate anti-clockwise. So when I rotate anti-clockwise, what will happen? This OH will come on the left side. So that is what I have drawn here, and correspondingly the other substance, that is your hydrogen, will be coming on this particular side of the molecule. So once you get this particular way of writing, what you do, you just have to put the crosses and put the substituents accordingly. Okay, so it is pretty simple, but this molecule is pretty simple, but if the substituents are a little bit complicated, it is not so easy to always visualize the perspective formula and see how the changes are happening. So that is why I'm saying that it is always better when it is multiple asymmetric centers to use Fisher project formula. Okay, so what we have studied is how we can convert a perspective formula into a Fisher projection formula. Now let me tell you one important thing, and I would like you to practice that. Now, when it comes to, we have seen this, that if I try to draw a mirror image of this particular Fisher formula, how it looks like, it would look like something like this. Okay, so this, as we saw in the last class, since it's a chiral molecule, the mirror image won't be superimposable on the original structure. So when I draw the mirror image of this compound is different from the original compound. So if I ask you how many stereoisomers are possible for this particular molecule with one asymmetric center, you will say 2 possible compounds, 2 possible different compounds you can make when you have one asymmetric center. So this can be understood using a formula which says about the number of stereoisomers possible. So that is given as equal to 2 to the power of n. Now n is the number of asymmetric carbon. Now in this compound, number of asymmetric carbon is only 1. There is only one asymmetric carbon in this particular molecule, because there is only one carbon which is attached to 4 different groups. So that is why this particular compound, if you are asked how many number of stereoisomers you can make out of compound with this with one asymmetric center, you will say only 2, because 2 to the power of 1 is just 2. So you can make only 2 stereoisomers. One is the original molecule and its mirror image. Okay. Now here in this compound you have how many asymmetric centers? You will have 2 asymmetric centers. Like if I number it 1, 2, 3, and 4, there are 2 asymmetric centers where the groupings are 4 different groupings are different. Now according to this formula, how many stereoisomers you can draw? 2 to the power of n. So in this case, n is 2. So approximately 4 stereoisomers you can draw for this particular molecule. So what I would like you to do is you go and make 4 different possible ways of writing this particular molecule. One molecule I'll show you. One possible way is to draw its mirror image. Mirror image would be what? CH3, CH3. I'm drawing the mirror image, okay? So you have the OH here, you have the H, you have the H here, and you have the OH coming here. So this is another. So 2 molecules have already come. Now draw another possible conformation. Now please keep in mind that you keep the carbon chain on the vertical bonds of the Fisher projection formula, because it is a convention that you keep the long carbon chain on the vertical bond and the substituents you keep on the horizontal bonds of the Fisher projection formula. So I hope you understood what I'm trying to say to you. So I would like you to make what all possible stereoisomers you can make for this particular molecule, that is 2,3 diol, 2,3-butane diol. Okay, so I have drawn 2 more stereoisomers you can draw. Please draw them, okay, and try to visualize whether you can make 4 stereoisomers or not. So with this, I would like to close this particular session. I hope you are understanding. If you have any doubt, please ask me. Thank you very much. Have a nice day.